Imagine two photons that, once created together, instantly share a secret connection no matter how far apart they travel. In this lesson we Eurostrade uncover how these quantum twins are made, how their mysterious link defies classical limits, and why the physics behind it still sparks debate among scientists. When a nonlinear crystal is pumped with a laser, it can split one high-energy photon into two lower-energy photons. These daughter photons are emitted in opposite directions and share a joint quantum state that cannot be described independently. The polarization of each photon is correlated so that measuring one instantly determines the other's orientation, regardless of distance. Mathematically, this relationship is expressed by a superposition of two basis states, such as HV plus BH. The coefficients in front of each term are equal, which guarantees that the photons always exhibit opposite polarizations. Because the state is shared, no local hidden variable can assign definite values to both photons before measurement. When a polarizing beam splitter analyzes one photon, its outcome collapses the joint wave function and fixes the partner's state. Even if the photons are separated by kilometers, the correlation appears instantaneously, a phenomenon Einstein famously called spooky action at a distance. Experimental tests using Bell inequalities have repeatedly ruled out local realistic explanations, confirming that entanglement is a genuine quantum resource. Thus, photonic entanglement provides a mechanism for nonlocal correlations that underlie protocols like quantum key distribution and teleportation. Pause 0.8. A continuous wave laser emits photons that are directed into a beta barium borate BBO crystal. Inside the crystal, the strong electric field of each photon can induce a nonlinear interaction that splits it into two lower-energy photons. Conservation of energy requires that the sum of the energies of the daughter photons equals the original photon Eurostrade's energy. Likewise, conservation of momentum dictates that their wave vectors must add up to that of the incident photon, leading to specific emission angles. The crystal Eurostrade's birefringent properties cause the two downconverted photons to acquire orthogonal polarizations in a correlated fashion. Because the process is coherent, the joint quantum state of the pair cannot be written as a product of individual states. This is the hallmark of entanglement. When one photon passes through a polarizer set at 45 circumflex degrees, its polarization becomes undefined until measurement, instantly collapsing the partner Eurostrade's state regardless of distance. By placing identical analyzers on both beams and recording coincidence counts, experimenters confirm that correlations exceed any classical explanation. The rate at which entangled pairs are produced depends on the pump power, crystal length, and phase matching angle chosen during alignment. Adjusting these parameters allows researchers to tailor the brightness and spectral bandwidth of the source for quantum communication protocols. In practice, a narrowband interference filter is often inserted after the crystal to select photons within a desired wavelength window. The resulting entangled photon stream can then be routed through optical fibers or free space links for remote tests of Bell inequalities. Pause 0.8. We begin by generating pairs of entangled photons through spontaneous parametric downconversion in a nonlinear crystal. Each photon travels to a distant station where its polarization is measured after passing through a rotatable polarizer. The angle of each polarizer can be set independently, allowing us to explore different measurement bases for the two photons. For every pair we record whether the detectors register a click or not, building up joint probability statistics over many trials. These probabilities are then used to calculate the correlation coefficient as a function of the relative angle between the polarizers. Classical physics predicts that this correlation should never exceed the bound set by Bell Eurostrade's inequality, which is 0.707 for ideal settings. When we plot our experimental data, we observe values surpassing this classical limit, reaching up to 0.85 in some configurations. The excess indicates that the measurement outcomes are not predetermined locally but instead exhibit non-local quantum correlations. By systematically varying the angles and repeating the experiment, we confirm that the violation persists regardless of spatial separation. Thus, the results provide strong evidence that photons share an entangled state that defies classical explanation. Pause 0.8. When a pair of photons is created in an entangled state, their quantum properties are linked by a single shared wave function. If one photon travels to detector A and the other to detector B, the two detection events can be arranged so that neither lies within the other's light cone. In such a spatia-Euros-like configuration, no signal traveling at or below light speed could inform one detector of the outcome measured at the other. Nevertheless, When experimenters record the outcomes, they find that the results are correlated in a way that violates any local Houdini-Euros variable explanation. The mechanism behind this correlation is not a physical influence propagating between the photons. Instead, it reflects the instantaneous update of the joint wave function upon measurement. When detector or registers a photon Euros trade as polarization, the quantum state collapses to a definite value for both particles simultaneously, regardless of distance. This collapse does not carry energy or information through space. It merely reduces the set of possible outcomes consistent with the shared entangled state. The observed correlations are quantified by Bella-Euros type inequalities, which the experimental data consistently exceed, confirming non-local behavior. By plotting emission and detection times on a spacetime diagram, one can see that each event lies outside the other's future light cone, yet their statistical link remains intact. Thus, entangled photons maintain non-local correlations even when separated faster than light could communicate, illustrating the fundamental non-classical nature of quantum mechanics. Pause 0.8. Entanglement links two photons, so that the measurement outcome on one instantly determines the outcome on its partner. In quantum key distribution, entangled pairs are distributed to sender and receiver, who each measure in randomly chosen bases. The BB84 protocol can be implemented with polarization-encoded photons. The sender selects a basis and records the bit value. After transmission, the parties publicly announce their chosen bases over a classical channel. When the bases match, the correlated measurement results form a shared secret key that is secure against eavesdroppers. Teleportation uses an entangled pair and a Bell state measurement to transfer an unknown photon state from sender to receiver. The sender performs the joint measurement on her half of the entangled pair and the input photon, collapsing both into a known outcome. She then sends two classical bits indicating the measurement result to the receiver. Using this information, the receiver applies a corresponding unitary operation to her photon, reconstructing the original state. These protocols illustrate how non-local correlations enable secure communication and faithful state transfer without moving matter. Pause 0.8. Quantum entanglement in photonic systems reveals correlations that persist regardless of spatial separation, challenging classical intuitions about causality. When two photons are prepared in an entangled state, measuring the polarization of one instantly determines the outcome for its partner. This phenomenon is quantified by violations of Bell inequalities, which rule out any local hidden variable explanation. It respects relativistic constraints, yet the mechanism that propagates this influence without a mediating signal remains an open question within standard quantum theory. One proposal attributes the effect to pre-existing correlations encoded at the source, but it cannot account for dynamic changes during measurement. Another view suggests that entanglement is a manifestation of non-separable Hilbert space structure, where joint states are fundamental rather than individual particles. The Copenhagen interpretation treats collapse as an instantaneous update of knowledge, effectively sidestepping the need for a physical mechanism. In contrast, many worlds eliminates collapse by positing branching worlds, but it still requires a rule that enforces correlated outcomes across branches. Hidden variable theories like de Broglie-Bohm introduce guiding waves that carry non-local information, yet they face challenges reconciling with relativistic covariance. Experimental advances in photonic entanglement such as loophole-free Bell tests and high-dimensional state generation continue to refine the empirical boundaries of these interpretations. Future research may uncover whether decoherence, contextuality, or a deeper layer of reality underlies the observed non-local correlations. Until then, the precise mechanism that links distant photons remains one of quantum mechanics' most intriguing open problems. Pause 0.8. We explored how nonlinear crystal splits a single photon into two entangled partners via SPDC, then saw how measuring their polarizations can violate Bella-Euros trade S inequality, confirming quantum predictions. Even when the photons are separated faster than light could communicate, their correlations remain intact to Euros, highlighting the non-local nature of quantum mechanics. Finally, we connected these phenomena to real Euros world technologies like secure communication and teleportation, while acknowledging that the deeper mechanism behind non-locality remains an open question.